So right now we are going to plot a vapor pressure composition diagram. In order to do that, we have to draw the axis of vapor pressure against mole fraction. Suppose that we have an ideal mixture of two liquids, A and B, and with A and B having their own vapor pressure. Okay, according to Raoult's law, the partial vapor pressure of A at a particular temperature is directly proportional to its mole fraction. So if you put a graph of vapor pressure of A against its mole fraction, you will get a straight line graph. If you double the mole fractions for A, you will get a double of its vapor pressure. Now we will do the same for B on the same sets of axes. Okay, we have here B, and as mole fraction of B falls, here when the mole fraction of B falls, the vapor pressure for B also falls. Okay, notice that the vapor pressure of B is higher than A, so meaning that molecule B is more volatile than A. It is easily to break away the bond. To get the vapor pressure of the mixture between A and B, we have to add the value A and B at each composition. The effect is that it will give us a straight line of total pressure. Previously, we have seen the vapor pressure composition diagram for ideal mixture of two liquids A and B. Right now, we are going to see the vapor pressure composition diagram for non-ideal mixture of A and B. They are divided into two, which are positive deviation and negative deviation. For positive deviation, the total pressure is greater than the predicted one by Raoult's law. Let's say we have an example here where the vapor pressure for B is less than vapor pressure of A. However, the addition of these two vapor pressure will have higher curve than the predicted one by the Raoult's law. And for positive deviation also, the intermolecular forces between molecule A and B is much weaker than the individual intermolecular forces of molecule A and molecule B. For positive deviation also, it will have delta H greater than 0, meaning that the molecule is absorbing the heat to form new molecular interaction, what we call as endothermic, and we also have delta V greater than 0. The volume is expanded when the mixing of components A and B. For negative deviation, we have the total pressure is less than the predicted one by Raoult's law. Here we have curve is less than the predicted one. And the intermolecular forces between molecules A and B is much greater than the individual intermolecular forces of molecule A and B. The delta H is less than 0, meaning that the heat is released or exothermic, and the delta V is less than 0, meaning that the volume is decreasing. So right now we are going to convert the vapor pressure composition diagram for an ideal mixture of A and B into boiling point composition diagram. In order to do that, we are going to plot boiling point against mole fractions, which consists of compound A and B. For mixture A and B, there will be a curve formation joining the boiling point of these two. Okay, why the boiling point of compound B is less than compound A? Because previously compound B have higher vapor pressure as compared to compound A. Higher vapor pressure meaning that compound B is more volatile than compound A. That is why the boiling point of compound B is less than compound A. And this diagram also shows that what happens if we boil a mixture of A and B at point C1 and at particular temperature, which is T1. So here is the point where the liquid boils at this temperature, and then the liquid will turn into a vapor at this point, and then there will be a condensation happen, so we can collect the composition of this mixture at C2. And if we repeat the boiling process, we can see that another composition which is C3. So this is what we call as also distillation process. So the vapor composition will be at this area and the liquid composition at this area. Fractional distillation is a technique to separate the liquid mixture containing two or more compounds that boils at different temperature. So the chemical compounds are separated by heating them to a temperature at which one or more fractions of the mixture will vaporize. So pure liquids will be collected as a result of the condensation from the distillation process. If we go here, let's say the boiling process here, and then the condensation happen, and then there will be another boiling process and the condensation happen, and then this point here is the approaching the pure liquids here. Let's say B, compound B, approaching the compound B here. So this one will be collected as the pure liquids, and then the liquid that has higher boiling point will remain as a liquid or residue after the distillation. This is an example of water alcohol system. We can see the boiling point composition diagram, which the boiling point of water is at 100 degrees C. So when we boil the mixture of water and ethanol at 20% here, we are going to see the boiling process at 90 degrees C, and the liquid turns into vapor at this point, and then we can collect the mixture when undergo condensation at this point, and then we boil again the mixture and repeating the process until we get the pure ethanol at 66 degrees C. Let's take a look at the simple fractional distillation in the lab. So the apparatus that we need for this setup is that we are going to have round bottom flask which connected to a fractionating column and then connected to a condenser, and then we are going also to have the adapter and the receiving flask. First, we are going to see the round bottom flask is heated using steam baths that allow mixture to boil. We are using steam baths to avoid direct heating, and then don't forget to add also boiling chips to avoid bumping. And when the liquid mixture is boiled and turned into vapor, we are going to see the condensation happen, where the vapor emerging from the top of the column is condensed to a liquid. And then later we are going to collect the compounds that contain the most volatile component here, or what we call as a lowest boiling point compound. And then the later fractions are less volatile liquids, which meaning that the least volatile compounds or the highest boiling point will remain as a residue in the distillation point. So here we have the fractional distillation in the industry. Example, here we have the oil and gas industry. So fractional distillation is one of the popular techniques, which principle behind the process is remain the same, and only that the distillation is carried out on a larger scale. So here we have a huge distillation column or distillation tower, and the industry in this case is using reflux to ensure the complete separation of the mixture. So here we have the crude oil, which consists of several compounds such as naphtha, gasoline, paraffin oil, diesel oils, and all, and etc. So they are separating this mixture by using this column. Okay, when the crude oil is added into the chamber or the column and heated using high pressure steam, the mixture will start to boil and the vapor is formed. The vapor will enter each of the separate plate here, so to form the individual compound, and various substances enter the vapor phase in several places. So at lower part of the column we have the high boiling point mixture or compound, and the top here we have the low boiling point mixture or compound. What is azeotropic system? Here we have a mixture of liquids that maintains its composition and boiling point during distillation. It occurs that when a mixture is boiled to produce a vapor that has the same composition as the liquid. So there are several types of azeotropic system. We have here the number of constituents, where the binary we call it as 2 liquids, ternary consists of 3 liquids. For hetero and homogeneous system, we have here hetero means that the liquids are immiscible, and the homogeneous means that the liquids are miscible. And in the system also we have the positive and negative. The positive azeotropic system is where the boiling point of the mixture is lower than any of its constituent, and the negative one is the boiling point of the mixture that is higher than any of its constituents. Okay, let's take a look at the positive and negative azeotropic. Here we have the point here where the boiling point of the mixture is minimum at this point. Okay, the boiling point of the mixture. And here we have the liquid plus vapor. The same goes for here, liquid plus vapor. So this is what we call as the positive azeotropic system, where the pressure for real mixture or non-ideal mixture is greater than the P ideal, and the temperature of the real mixture is less than the temperature of the ideal. And for the negative azeotropic system is in the opposite way. We have here the maximum boiling point of the mixture. Here we have the composition of liquid plus vapor. Here also we have the composition of liquid plus vapor. So the negative azeotropic system will have the pressure is less than the ideal, and the temperature of the real or non-ideal mixture is greater than the ideal.